All right, let's jump right in. We live in a world that is just full of facts. They're messy, they're complicated, and honestly, a little overwhelming. But then science comes along and gives us these beautiful, clean, elegant theories. So the question is, how do we get from one to the other? That's what we're going to unpack today, this incredible journey from raw, messy reality to a clear, refined understanding.
It really all boils down to this one classic question. You've heard the story, right? How does something so ordinary, so specific, like an apple bonking Newton on the head, somehow become a universal law of physics, a law that doesn't just govern apples, but planets and stars and entire galaxies? What's the secret ingredient? What happens in between?
And this, right here, just shows you how huge that gap is. On one side, you've got the raw fact, a real apple. It's got color, a specific texture, little bumps. It's a unique thing. And on the other side, a totally clean, incredibly powerful, and, well, abstract formula. They seem like they're from different universes, but somehow one gives birth to the other.
To really get this, we have to start at the beginning. The world doesn't just serve us up neat little facts on a platter. No, what we get is something some thinkers call the entropy of experience. It's just a chaotic flood of information, of sensory input, endless details. It's pure noise.
So you can see why science can't just be about collecting facts. That would be like trying to collect the entire ocean in a bucket. The real genius of science is that it builds a structure, it builds a bridge to get us from that noisy, chaotic shore of raw experience over to the solid, quiet ground of real understanding.
And that bridge, it's built using one master tool. And that tool is abstraction. This is the whole game. This is how we carve a clear path from the chaos of the world to the clarity of a theory.
But what is abstraction, really? Well, think of it as the engine of science. It's this whole process of taking all that messy, real-world stuff and then translating it, filtering it, and reshaping it into the clean, formal language that theories are made of.
Okay, so the first tool we pull out of our toolbox to build this bridge is something called idealization. Because, here's the secret, to understand reality, sometimes you have to simplify it first. Let's go back to our apple. A real-world apple is insanely complex, right? It's got a specific shade of red, a certain texture on its skin, a unique shape with little bumps, the stem has a length, it has a smell, and of course it has mass. There are dozens, maybe hundreds of things we could measure about it. But then a physicist comes along, looks at that falling apple, and does something absolutely radical. They ignore almost everything. The color? Doesn't matter. The smell? Who cares? The bumps? Nope. They simplify that entire complex object down to one single essential feature for this problem, its mass.
And that move right there, that has a name. It's called idealization. It is the deliberate, intentional act of stripping away all the extra complexity so you can isolate the one or two variables that actually matter. It lets you see the core principle at work without getting lost in all the noise. And it's not just physics. Economists do this all the time with their idea of a perfectly rational actor.
So once we've simplified our fact, what's next? Well, we have to translate it. We need to take that idealized thing, our mass, and fit it into the formal language and structure of a scientific theory.
I absolutely love this quote from the source material. It nails the goal perfectly. The point isn't just to look at facts from a distance. The goal is this immersion, where you integrate the facts so deeply into the theory that it becomes a part of the theory itself.
And this gets at something really crucial. This whole process is active. Scientists are fitting the data into their models, and sometimes this even means deciding to set aside some data, maybe an outlier that doesn't fit a rational model, all in the name of building a framework that's more objective and more precise.
But look, if we're going to build this bridge of abstraction, it has to be strong, it has to be reliable, it needs some solid engineering principles. So let's look at a couple of the most important ones that hold the whole thing up.
First up is something called the abstraction of identification. Now, that sounds super academic, I know, but trust me, it's something you do 1,000 times a day. It's just the active choice to treat different things as if they were the same, so you can lump them together into a useful category. I mean, just look at these things. You've got a hard wooden stool, a rolling office chair, a squishy beanbag. In reality, they're wildly different objects, right? But through this abstraction of identification, we make a decision. We decide to ignore their differences and group them all into one useful category, chair. Science does this constantly to create general rules.
Now, this second principle is really sophisticated. It's called the interval of abstraction. And this is the deep understanding that scientific ideas aren't these perfect razor-sharp points. No, they're more like ranges or intervals that cleverly build in the fact that the real world has uncertainty and error.
So imagine we go to measure the boiling point of water. We might be tempted to just write down a single perfect number, 100 degrees Celsius. It looks so clean, so absolute, so certain.
But a scientist knows that's not the whole story. A much more honest, and you won't believe this, a more precise measurement would actually include the margin of error. See, acknowledging that uncertainty, that little interval, that's not a weakness. It's actually a higher form of precision because it's being honest about the limits of what we know.
So, at the end of the day, what's the big payoff? Why do we go through all the trouble of building this bridge of abstraction? Well, it's pretty huge. It's what allows us to take the chaos of reality and simplify it. It's how we achieve incredible levels of precision. And ultimately, it's how we build the powerful, testable theories that are the bedrock of all modern knowledge.
And that leaves us with one last kind of mind-bending question to chew on. We've just seen that science is this powerful tool for making simplified models of the world. But if every single theory we have is an abstraction, a simplified, idealized translation, then what is the real, unabstracted world actually like? Something to think about.